So we have problem number 14 in the Advanced Classical Mechanics practice final exam. So a particle of mass m scatters off a repulsive potential V of r equals beta over r cubed, where beta is greater than 0. Part A, derive the orbit equation in terms of u equals 1 over r. Part B, express the scattering angle as an integral over r or u. Part C, determine the distance of closest approach in terms of energy E and angular momentum L. Part D, analyze the high energy small deflection limit. And part E, compare qualitatively with Rutherford scattering from a 1 over r potential. So this is a central force scattering problem. So the potential is V over r equals beta over r cubed, where beta is greater than 0. So the force is going to be F sub r equals negative dV dr equals 3 beta over r to the fourth. So this is going to be repulsive in points outward. What we're going to do here, we'll let u equal 1 over r. And the Binet equation is second derivative of u with respect to phi plus u equals negative m f sub r over L squared u squared. So since f sub r equals 3 beta u to the fourth, then the second derivative with respect to phi plus u equals negative 3m beta over L squared times u squared. And using energy conservation here, E equals 1/2 m r dot squared plus L squared over 2m r squared plus beta over r cubed. So building on that here, the effective potential is V sub E f of r equals L squared over 2m r squared plus beta over r cubed, where the distance of closest approach, that's r naught, occurs when r dot equals 0. So E equals L squared over 2m r naught squared plus beta over r naught cubed, and equivalently E r naught cubed minus L squared over 2m r naught minus beta equals 0. So the scattering angle can be written as chi equals pi minus 2 times, so pi minus 2, and then integrated here, and our integral here is LdR over r squared times the square root of 2m times the square root. Let me read that again. Sorry about that. The integral here is from r naught to infinity. LdR divided by r squared times the square root of 2m times that quantity E minus L squared over 2mr squared minus beta over r cubed. So equivalently, in terms of u equals 1 over r, chi equals pi minus 2 times this integral from 0 to u naught du over square root of 2m e over L squared minus u squared minus 2m beta over L squared u cubed, and that is where u naught is equal to 1 over r naught. So building on this, moving on. Okay, so we have for high energy or large impact parameter, the deflection is small. We're going to let E equals 1/2 m v at infinity squared and L equal m v at infinity times b. Using the straight line approximation, r of t is approximately square root of b squared plus v at infinity squared t squared. And the transverse force is going to be F sub perpendicular equals F sub r b over r equals 3 beta b over r to the fifth. So the transverse impulse is going to be delta p sub perpendicular equals this integral from negative infinity to infinity, 3 beta b dt over the quantity b squared plus v at infinity squared t squared raised to the 5/2. So using this integral, negative infinity to infinity for dt over the quantity b squared plus v at infinity squared t squared raised to the 5/2. That's going to come out to, performing the computation, 4 divided by 3 v at infinity b to the 4th. And we're going to get delta p sub infinity equals 4 beta over v at infinity b cubed. So from here, the scattering angle is chi is approximately delta p subperpendicular divided by m v at infinity. Therefore, chi is approximately 4 beta over m v at infinity squared b cubed. And since here E equals 1/2 m v at infinity squared, this becomes chi is approximately 2 beta over e b cubed. So we could say, so the high energy small deflection limit is going to be chi is proportional to 1 over e b cubed. And compared with Rutherford scattering from a 1 over r potential, we have these bullet points here, these 4. 1 over r scattering gives a long range force in a deflection scaling like 1 over E times B. This 1 over r cubed potential is a shorter range. Its force falls as 1 over r to the 4th. Excuse me, sorry. And its small angle deflection falls much faster as 1 over EB cubed. So our conclusion here is beta over r cubed gives a repulsive short range scattering problem with our chi here being asymptotically equal to 2 beta over EB cubed in the high energy limit, or we could say approximately equal to 2 beta over EB cubed in the high energy limit. Okay, so that's all for problem number 14. Thank you very much and have a great day.